Okay, YouTube, in this video we're going to continue looking at solving rational equations or equations involving rational expressions, but specifically in our last video we looked at rational equations that we said were proportional. That is to say that we're a single ratio equal to another single ratio when we don't have something like this, like perhaps if we had, plus 1 over f or something like this here. We cannot use cross products to solve it, and so our method instead is going to be to use what we call, I guess, the least common denominator. And so looking at it this way, we can actually, to solve an equation that is not expressed as a proportion, we can solve it by multiplying each side of the equation by the least common denominator of rational expression. So in other words, we could basically take both sides of this equation right here times the least common denominator. Then what would happen is we would wipe out the denominator completely. So let's just put it this way. In this expression here, our least common denominator would just be b to the first, d to the first, f to the first. And if we were to take both sides times this set of factors here, BDF, BDF. What I want you to see is that our b's over here would just cancel out, and what we get left with on the left side would be ADF. On the right side, if we were to distribute this through, you would see that in the first case, our d's would cancel out, and we'd get left with c times b times f, CBF, plus now, bring down the plus. If we take BDF times this 1 over f, the f's would cancel out, and we get left with just 1 times BD. So this was highly symbolic here. What I'd like to do is just give a more concrete example where you maybe solved equations before look like this. And so hopefully you've got a math teacher that says, hey, you know what you want to use? You want to use the least common denominator, which is the least common multiple of all of our denominators here. So if we were to choose a least common multiple of 2, 3, and 12, of course 12 would be the one that we're looking for. But looking at something like this, again, what I want you to see is if we were to take both sides times the LCD, the neat thing about the LCD, which is the least common multiple of all of these things here, is that if you factor it, like 12 is 2 times 2 times 3, 2 is a factor of that, 3 is a factor of that, 12 is even a factor of this. So when you multiply through, because 2, 3, and 12 are factors of the LCD, then what you're going to get to happen is you're going to get things to wipe out completely in the denominator. So here we have our 2 and our 12 cross-canceling. The 2 would become a 1, the 12 would become a 6, and we'd end up with 6 times 1 times x. So really we would get just a 6x here. And if we take 12 over here times this 1/3, the 3 and the 12 cross reduce, okay? And we get 1 and a 4, so we get 4 times 1, so we say plus 4. Now on the right side, 1 12 times 12, well these 12s would just straight up cancel, we just get left with 1. So to solve something like this would be a lot more straightforward. As a matter of fact, we could just solve this using traditional techniques here and isolate the x value. So we get a negative 1/2 in this case here. We could definitely check this by plugging it back in. I'd really rather just point out the fact that the method we could use here is just to multiply both sides of the equation by the least common denominator. And that also works with cross product worthy problems. If you do have a proportion, you can do that. But if you don't have a proportion, you certainly must do this here, or at least it's the prevailing method. So let's take a look at a couple of examples here in which we have not just a fraction equal to a fraction, but we have like a sum of two fractions equal to a fraction and a difference of two fractions equal to a fraction. So looking at this letter A first, the first thing we want to do is assess the situation and say, hey, what's our least common denominator? Because that would be the least common multiple of x, 4, and x if they're completely factored, which they are. So to list out our LCM list here, we have the highest power of x is x to the first, and our highest power of 4 is 4 to the first, and we've already listed our x to the first here up on our list. So we say our least common denominator is 4x. The least common denominator is just 4x. So what we're going to do is we're going to take 4x times everything on the left, and we're going to take 4x times everything on the right, and what we see happening here is this 5 over x and 7 over 4, and this negative 9 over x. As we multiply or distribute here, we're going to see that some of these factors cancel out. So for instance here, 4x times 5 over x, this is tantamount to saying that the x's would cancel out. We get left with 4 times 5. Really, we get a 20 there. Plus now 4x times 7 over 4, the 4 would cancel out with this 4, and we just get left with 7x. So for the left side, we have 20 plus 7x, no denominators any longer. And on the right side, this x here would cancel out with this x here, we get left with a negative 36. So to solve this, pretty traditional problem here, we would just go ahead and isolate the x variable afterwards. So we say 7x equal to a negative 56, and dividing both sides by 7 here, of course, we would come up with x equals a negative 8. And so it's always a good idea to check your solutions by plugging this back in. It's also always a good idea to find any restricted values of x that you would see here. And I see that x would not be allowed to be equal to 0, but that's not a problem here because 0 was not one of the algebraic solutions that we found. So that's what it looks like when we use the least common denominator. Let's take a look at another example where one of our terms is actually just a whole number term. And so the first thing I'd like to do is just go ahead and write this as a ratio by putting a 1 underneath it, and then looking at what our least common multiple of all of our factored denominators would be. So 1, well, you don't have to list 1 as a factor because 1's a factor of everything. X minus 5, the highest power of x minus 5 is x minus 5 to the first, so we have x minus 5 to the first. And then x occurs, and the highest power of x is x to the first. So our least common denominator is going to be x minus 5. And as we take both sides times this, so I'm going to write this out. We say x times x minus 5 times everything on the left, which is this 1 over 1 minus 8 over x minus 5. Okay? And we're going to take x, let me do this here. We'll put the 3 over x here. Brackets and parentheses, they mean the same thing, so don't worry about the differences here. So we'll go ahead and distribute this through. Now, first things first, on the left side here, anything times 1 is itself. So x minus 5 times 1 over 1, nothing cancels, and we just get x minus 5. Now, when we take x minus 5 times 8 over x minus 5, I want you to see that your x's minus 5 cancel out, and we get left with 8 times x, so 8x here. And then on the right side, our x's cancel out, and we get left with 3 times x minus 5. So the way this works is a little bit more involved than the last one, is that we need to simplify both sides first. So that means distribute, combine like terms. We get x squared minus 5x here, minus 8 more x's. On the right side, we get 3x minus 15. And so what I'd like to do is go ahead and let's combine these two here. We get x squared minus 13x's equals 3x minus 15. And because we have an x squared and an x to the first, chances are we're going to need to go ahead and set this equal to 0, and we'll just solve this by factoring. So take away 3 more x's, add on 15 constants. What we're going to end up with here is this. We end up with, on the left side, x squared minus 16x's to the first plus 15 constants equals 0. And as I consider this here, I suppose, I would say that two factors of a positive 15 that have to be a negative 16 are a negative 1 and a negative 15 here. And so what that means for us is that we get two solutions. We get a 1 and a 15. Okay. And in terms of restrictions up here, I noticed that x minus 5 equals 0 if and only if x equals 5. And I noticed that x equals 0 if and only if x equals 0. So with these being our restrictions, we just want to check to see that we didn't get any restrictions algebraically on our list of solutions. And we certainly did not. And it would be a good thing to plug both of these back in to check to see if they work. So what I'd like for you to try now, I suppose, as I left 3 examples here, is go ahead and assess the situation in each of these. Say, what is our least common denominator? Run through and multiply both sides by the least common denominator and see what you end up with here. When you're ready to check out the solution, at least for number 6, go ahead and unpause the video. So really quickly here, let's take a look at number 6. What I want to point out here on number 6 is that when you look at your denominators, we have 4x plus 1 over x plus 1. And this is equal to 12 over x squared minus 1. The thing I want to point out is that in order to find the least common denominator or the least common multiple of all of our denominators here, we have to list everything as a ratio. That includes putting this 3 over 1, and we have to have everything factored. So in terms of least common multiple here, suppose a least common multiple, we see that x plus 1 is at most to the first power in any of our denominators. So we have x plus 1 as one of our factors here. X minus 1 occurs, and it is at most to the first power in any of our expressions, and 1 occurs here. So our least common denominator is just the product of these two, and it's good to leave these factored because what we're going to do, of course, is take both sides of this expression times x plus 1, x minus 1. So I want to show you this here, see if you get the same thing that I did. X plus 1, x minus 1. And as we multiply this through on the left side, the x plus 1's cancel out. We get left with x minus 1 times 4x plus 1. So we're going to need to FOIL here. And as we distribute across this way, we can see that at least with 12 over x plus 1, x minus 1, these would both cancel out with these. And we would just get left with a 12 here. Let me write that in green. 12 plus now 3 over 1, nothing's going to cancel out. So we get left with 3, x plus 1, x minus 1. So a little bit more involved this time. Let's go ahead and FOIL on the left-hand side. We get 4x squared plus x minus 4x's minus 1. And on the right side, we have 12 plus. Now, what I want to recognize is that this right here, let's go ahead and make a note, this is really 3 times x squared minus 1 because when you multiply out these two conjugate pairs, you get a difference of squares. But that being said, 3 times x squared is 3x squared, and 3 times a negative 1 is a negative 3. Let's go ahead and combine any like terms that we can. That includes over here on the left side, positive 1x and negative 4x, you get a negative 3x. This is a squared x here. Minus 1 on the right side, it looks like we have just 3x squared. And if we combine our 12 and our negative 3, we get a plus 9. So the last thing we're going to want to make sure we do here is set this equal to 0 and factor it. So I'm going to subtract 3x squared and 9 from both sides. So taking away 9 and a 3x squared, it looks like we get left with a single x squared on the left side. This is minus 3x's to the first. This is minus 10 constants, and we cleared the right side. So in terms of factoring this, I do believe this does factor. And we get x minus 5, x plus 2 here, which gives us two x values here. It looks like we get a positive 5 and a negative 2. And so looking at our initial expression here, our denominators, when we factored them, were x plus 1, x plus 1, x minus 1, and a 1. We would say that x is just not allowed to be a plus or a minus 1 because that would cause these two factors to equal 0, or this one factor to equal 0. But neither of those plus or minus 1 values was on our list of solutions, so we don't need to lose any of the solutions that you found. So hopefully you got that. In the next video, we'll look at some examples, including what we call extraneous solutions. Cheers.